Hello, good morning. This is a live session for the NPTEL course called Behavioral Theory with a View Towards Data-Driven Control. We are here to answer your queries if you have any. The students already know that they are supposed to ask their questions on the chat box, right? We have a couple of offline questions. I would answer those. I would like to answer those questions first while we are waiting for any live questions to come. The first one is, how is persistency of excitation related to subspace identification? Well, that's a very good question. See, when we do subspace identification, um, there are several techniques of doing subspace identification for mostly LTI systems given in state space form. I mean, assuming that the data is coming in the from state space realization of a system. If you look at it carefully, you'll find that in those techniques also, when you form the data matrix, you need to invert these matrices, because essentially you're going to compute some projections onto some specific subspace. You have various matrices like the input matrix, the output matrix, yeah, and then you sort of partition those matrices into like top rows and bottom rows, and then you do a projection of one matrix onto the row span of the other matrix. Yeah, such projections often involve uh, some uh, some sort of, for those projections to be well defined, well posed, you need some rank conditions to be satisfied, and those rank conditions actually are the persistency of excitation conditions in disguise. Okay, so in that way, depending on the technique that you are using for subspace identification, you will have these rank conditions to be satisfied, and those rank conditions are the ones which can be called persistency of excitation. See, essentially, our persistence of excitation also is, as I said, essentially a rank condition. Yeah, you look at the input and then you form that Hankel matrix out of the input, and that Hankel matrix must have full row rank, and that's the persistence of excitation. So there, for subspace identification, also you'll have such a full rank condition to be satisfied, which is the persistence, which can be called the persistence of excitation condition. Now, having said that, there are also other identification techniques. They're not like subspace identification per se, but utilizes some, utilizes singular value decomposition mostly, but once again uses data. So one of the most popular techniques of doing identification, system identification, is this Ho-Kalman algorithm. Yeah. Now, Ho-Kalman algorithm, let me tell you what Ho-Kalman algorithm is. Ho-Kalman algorithm looks at the impulse response data on the system. Yeah, input, only output, and that output is coming from the impulse response. Then you assume that the system is some controllable system which is generating, controllable observable system which is generating this data. Yeah, input is impulse, and output is that impulse response. Now, Ho-Kalman actually can find out those ABCD, minimal realization ABCD matrices, by looking at the impulse response data only. Now, that seems a little counterintuitive, because impulse, if you check, is not persistently exciting. Just impulse is not persistently exciting. And therein lies, I mean, it appears like a paradox that even if the input is not persistently exciting, how is it possible that we are getting a minimal realization? How is it possible that we can identify the system? So there, if you look closely at Ho-Kalman algorithm, Ho-Kalman utilizes the fact that it's an impulse response. It knows that it's an impulse response. Yeah. And importantly, because it's an impulse response, from there it calculates the ABCD matrices. Yeah. And you see, unlike the system identification that we have done in this course, where we look at the most powerful unfalsified model, MPUM, Ho-Kalman does not give you the MPUM. It gives you the state space minimal realization, which is for which this is the impulse response. If you apply MPUM, if you want to find out MPUM to an impulse response, the MPUM technique will mistakenly think the input, which is the impulse, as some sort of state trajectory which is arising out of some initial condition. Yeah. So if you look at an impulse response and then calculate the most powerful unfalsified model, you will get a system, yeah, which has no impulse. An autonomous system will the MPUM technique will result in an autonomous system. Yeah, as opposed to an input-output system that you get in Ho-Kalman. So that's the key difference between the Ho-Kalman technique, system identification technique, and the MPUM technique. That Ho-Kalman does not compute the MPUM, but rather it assumes the knowledge that this data is generated by an impulse response, and it utilizes that knowledge that it's an impulse response to come up with this ABCD matrices. So there you don't need any persistence of excitation kind of requirements. Only thing that you need is controllability and observability, right? I hope that answers your question. If you want to learn more about the connection between the kind of things that we have done for persistency of excitation with MPUM and subspace identification techniques, I think the textbook that we had referred to, yeah, exact and approximate modeling of dynamical systems by Markovsky, Willems, Bart Dimore, and another person. Yeah, that is the book. I think the 8th chapter of that book you can consult. Yeah. The second question is another very interesting question. Since behaviors are based on set theoretic formulation of trajectories, can a notion of convexity be related to these trajectories? Of course. But you have to realize that, when you're talking about this behavior as a set, which is in fact a subspace of an infinite dimensional vector space, each trajectory is a point. So when you talk about convexity, you are talking about connecting two points, right, by a line segment, straight line segment. Here it would mean that you are connecting two trajectories. You're going from one trajectory to another trajectory, yeah, by taking a convex combination of them. Now, going from one trajectory to another trajectory means that you're agnostic about the time. Yeah, you're not thinking of time as the only parameter. You introduce another parameter which makes you go from one trajectory to another trajectory, but not in time. In that how to explain that, in that parameter space. Yeah. So suppose W1 is a trajectory, is a full-fledged trajectory for all time. It is there. Yeah. It's a mapping from R to R to the power Q. That's W1. Likewise, you have W2. And suppose both W1 and W2 are satisfying some differential equations or difference equations. Yeah. And then you're saying that, is it possible that the behavior is such that lambda times W1 plus 1 minus lambda times W2, when lambda lies between 0 and 1, is this also a trajectory? If that is so, for every W1, W2, you say that this set, the behavior is convex. And you see the kind of things that we have seen, convexity will follow immediately, because things that we are talking about here, these W's, which are coming from behavior, the behavior is actually a linear vector space. And lambda plus 1 minus lambda times W1 plus 1 minus lambda times W2 is a linear combination. It's a convex combination. It's a special case of a linear combination, right? Because it's a linear combination and this is a vector space. The behavior is a vector space because a solution set of a linear system of differential equations with constant coefficients. It turns out that the set is vector space, and every vector space by definition, automatically is a convex set, right? So therefore behavior also will be convex. Yeah, but in general, if you look at general collection of excuse me. If you have a general collection of trajectories, there is no reason for it to be convex. Yeah. But the kind of behaviors that we were looking at, which are solution sets of linear ordinary differential equations or ordinary difference equations with constant coefficients, that's a linear vector space. And so automatically it's a convex set. Okay. Thank you. Thank you so much. Yeah, there's this other question also. Very good question. It says, what is the advantage of looking at the controllability from the behavioral point of view? Well, so first thing, when you define controllability, from the state space point of view, you see, it depends on the realization. Yeah. So let us try and make this distinction between a system and its realization. A system is there, some equations are there, which you may have derived from your physics, or you may have identified the model from input-output data. Whatever you have done, you have a system. Yeah, a system's equation. So for us, we take systems to be a collection of equations, right? And now there is this state space realization of that, which is a very special kind of equations which give rise to the behavior that we are interested in. Okay. Now, because controllability in state space is defined using the state variable, yeah. And so because controllability in state space is defined using the state variable, it appears that the property of controllability is not intrinsic to the system, but rather it's a property of the realization. You're getting my point, no? Given a system, a system of equations, linear equations, let's say, linear differential equations, and then a system of linear equations, and then we have this state space realization. Because the state space controllability is defined using the state variable. Remember, it says that you can go from any initial state to any final state in a finite amount of time by giving a piecewise continuous input. That's the definition of controllability. It appears that as if it's a property of the realization, because a same system, one system of equations can have two completely different state space realizations, one of which is controllable, the other is not controllable. So it appears as if this property of controllability is not a property intrinsic to the system, but rather it's a property of the state space realization. And no wonder that once we have done that state space realization and we have obtained those ABCD matrices, the controllability test comes via those that AB pair. And it depends on the AB pair, right? What AB pair you get. Completely different AB pairs can give rise to the same system. Same system can have different state space realizations with different ABCD matrices. So that's a bit unsettling, because we know, from various studies like structural controllability and stuff, that controllability is a property that is innate to the system, intrinsic to the system, and not a particular realization of the system. Yeah. Behavioral theory, the behavioral point of view of controllability, for the first time brings in this, makes this idea of controllability intrinsic to the system. The system's equation, yeah. You write the system's equation, could be higher order, doesn't have to be state variable equations. Yeah, fundamental principles are applied to obtain those equations, or perhaps some system identification has been done to get those equations, but the starting point is those equations. Yeah, and using those equations, whatever solution set you get, that's your behavior. And the question of controllability is directly imposed, directly the property of controllability is directly defined on that collection of trajectories. That's the advantage of having a behavioral approach to controllability, to controllable systems. Yeah, and then once you have obtained controllability, so that's from a more fundamental sort of point of view. The benefit that I just mentioned is from a rather fundamental point of view. When it comes to like some, whether there are utilitarian, is it really more useful to define controllability using behavioral theory, using behavioral approach? Even there, it turns out that it is so, because once you have controllability, you have this algebraic formulation of controllability in behavioral theory, like left co-prime and factor left prime. So the matrix, the kernel representation matrix is going to be full row rank, must be factor left prime. And once you have factor left primeness, that is equivalent to having an image representation. Once you have an image representation, that is like having a full parameterization of the trajectory of the behavior as an image representation. Once you have an image representation, it's parameterization, solving problems like LQ or optimal control becomes absolutely easy. Yeah. So from an utilitarian point of view, also behavioral theory approach to controllability is quite fascinating and quite appealing, I would say. But there are also, what should I say? There are obvious problems also. Like when you have state space controllability, I mean, it's a general sort of critique of behavioral theory in comparison with state space theory, because state space theory has this immense power that everything can be done in in the linear algebraic framework. You have only matrices to deal with, constant matrices, A, B, C, D matrices to deal with, all sorts of strong techniques like Krylov subspace, Gram-Schmidt orthogonalization, all sorts of singular value decomposition, all these immensely powerful computational tools are at your disposal when you are handling a dynamical system from a LTI dynamical system from a state space point of view. On the other hand, if you are handling a dynamical system from behavioral theory point of view, then techniques, the computational techniques are not as strong, as refined, as powerful as this linear algebraic computational techniques. There are many techniques that can be employed here. Here, essentially, you have to use polynomial techniques, right? Like symbolic computational tools you have to use. They are quite powerful these days. And with larger computing powers, GPUs and stuff, it is in fact becoming more and more powerful almost every day. Techniques like Grosvenor bases, those can be employed to deal with behavioral theory, computational aspects of behavioral theory. But I would say that they are still not as powerful as linear algebra computational. Yeah, that's the drawback. I hope that answers your question. Thank you. Okay. There is a live question by Mr. Manoranjan Praharaj. Yeah, thank you for the question. It says, could you please let us know what is compactly supported set? Well, you don't talk about compactly supported set, but rather you talk about compactly supported trajectory. What is a trajectory? A trajectory is a mapping from from a set which is its domain, yeah, to a set which is its codomain. Yeah, suppose W is a trajectory, and I say that W is a mapping from R to R to the R to R, let's say. Then it's a real valued function defined on real numbers. Right? Now, in this particular case, what is the support of this function? So every function has a support. What do you mean by that? So because W is a mapping from R to R, yeah, or for that matter from any set to R, then you can ask this question, you can collect all those points X in the domain for which Wx is non-zero. Wx is a real number, right? So it's legitimate to ask the question whether Wx is zero or non-zero. So take W and collect all those x's in its domain so that Wx is non-zero. That set is called the support of this function. Okay. So this support is a subset of the domain. Now, once you have some topology defined on the domain, you can ask the question whether this set is a compact set or not. Yeah. If you have Euclidean vector space R to the power n as your domain for W, which R is a particular example of, which is what we had dealt with in this course. So if you have W mapping from R to R, look at all x's in R, all real numbers x for which Wx is non-zero. That's a subset of the real line. If that subset is closed and bounded, then it's called a compact set. And such a function whose support is compact is called a compactly supported function or a compactly supported trajectory. As simple as that. I hope that answered your question. Thanks. Yeah, there are two more questions, I think. One more question from Mr. Manoranjan Praharaj. It says that how this framework is related to data-driven control. Where is the link, sir? Okay. Um, so data-driven control, one of the basic requirements for data-driven control is the idea of persistence of excitation. So remember what data-driven control, this approach to data-driven control does. See, this is distinct from reinforcement learning type of data-driven control. Yeah. So here, what we have is we have a system which is like a black box. Yeah, we don't know the equations that are governing the behavior of the system of this black box. We only have input-output data. And we are allowed to run experiments on this system in terms of giving some input and output, yeah, and measure those input output. Now, once you have those input output, you design a controller to achieve some control objective of this system without actually having to find out the system's equations first. That's the idea of data-driven control. Yeah, one of these control objectives may in fact be identification of the system, right? Once you have identified the system, all control techniques can be used to get your objective, to get the objective of, getting some specified closed loop control system. Okay. Now, having said that, the question was, what is the link between this behavioral approach and the data-driven control. So the link is the following. Behavioral theory is the one that has been used. I mean, the techniques that we have learned in this course, or you will be learning in this course, these are the techniques which was used to come up with the proof of this persistency of excitation. See, persistency of excitation is a fundamental lemma. It's called the fundamental lemma, in fact, of data-driven control. So you have your input-output data, and you ask this question that, is this data sufficient for me to do the control? Is this data sufficient? Is my control objective achievable with this amount of data? Yeah. the uh, the basic thing that you can hope for or wish for from the data is that it's persistently exciting. If it's persistently exciting, then you can do almost everything that you want to do with the system. I mean, almost by that I mean that if instead you had the system's model itself, whatever you would be able to do, same thing you would be able to achieve if you have persistently exciting data. Yeah. Now, how do you come up with the proof? How do you understand this idea of a persistently exciting data? That was the link that that is the key that is provided by behavioral approach. And that's why we were interested in doing this behavioral approach to understand data-driven control. So in short, in a nutshell, data-driven control has is pinned, yeah, it revolves around, is pivoted around the idea of persistently exciting data. Yeah, this link or this pivot that persistently exciting data allows us to do everything that we would like to do. This philosophy is made clear through this approach called behavioral theory to dynamical systems. That is what we have tried to explore in this course. Yeah, I hope that answers your question, Mr. Praharaj. We have another question from Mr. Gautam Sinha, and he says, can you help me with week 1 question 2 and how to proceed with it? I am so sorry, I don't have the information on my fingertips right now. What was week 1 question 2? I really have no idea right now. What I would suggest, it's okay, let's do it this way. What I would suggest is you can write an email to me. I think my email address and other contact informations are available with NPTEL. You can write an email to me, or you can just search for my name, go to my webpage. I have get my email ID over there. So you can send me an email and I can resolve your doubt by email. Yeah, Mr. Sinha, does that work for you? And thanks, Mr. Praraj, for your questions, and I'm happy that I could answer them. Mr. Sinha, I hope that works for you. Thank you. Okay, one more question. What is a polynomial ring and how it is important? Well, let me first explain what is a ring. To understand that, we need to understand what is a field. So they are one of the basic objects in algebra. So not linear algebra per se. Yeah, the the branch of mathematics called algebra. See, when you have a set, yeah, where two operations are defined, okay, which are called addition and multiplication, then you know, a field means I'm being no, I'm not giving you a formal definition of it. I'm just giving you the idea which will which will make these concepts clear. Yeah. Um, so a number set of numbers where two operations are defined, and on that set, if you can do all four operations of arithmetic, then that set is called a field. Yeah, that's the rough idea behind the concept called a field. Let me give you an example. Hmm? The real numbers, a set of real numbers is a field. Yeah, why is it a field? Because you can add two real numbers and get a real number. You can subtract two real numbers and get a real number. You have a zero over there. Yeah, and for every zero has the property that for every real number, if you add zero to it, you get back the same number, right? And for every real number, there is another real number, which when added to it, gives you the identity that is zero. The additive identity is zero. So there is addition, and there are all these properties for addition. Yeah, the set is closed under addition. The set has a additive identity. Okay, and every element in the set has an additive inverse. Likewise, there is multiplication. If you take two real numbers and multiply them, you get another real number. So it's closed under multiplication. There is a multiplicative identity called 1, which when multiplied to any real number gives me the same real number back. That's the additive identity. And for every non-zero real number, there is also a multiplicative inverse. That means if x is a real number and it is non-zero, there exists another real number y such that x times y is equal to 1, the multiplicative identity. Okay, and then this addition and multiplication are sort of, when you have these properties, there you should ask things like whether it's associative, commutative, whether one distributes over the other. Yeah, those nice properties are also there. All commutativity, associativity, distributivity properties are also there. Then this set is called a field. As I said, real numbers is a field. There are many other examples of a field as well. Like, for example, the set of rational numbers is a field. Yeah, indeed. You don't have to go all the way up to real numbers. If you just look at two, ratios of two integers, yeah, the bottom one being the denominator one being non-zero, then that actually, if you look at all such numbers, it's a field. Yeah, we often denote it by the letter Q. That's the field of rational numbers. Not just that, look at rational numbers. Yeah, and then look at all expressions of the form alpha plus root 2 times beta, where alpha and beta are rational numbers. Look at all such expressions. I hope you remember from your high school math that you had done things like this and you called it surds, right? Surds. So alpha plus root 2 times beta. Yeah, that's a field. All such numbers of the form alpha plus root 2 beta, where alpha beta are rational numbers, is a field that contains the field of rational numbers. Not just that, replace root 2 by root 3, that also is a field. Yeah, this is called attaching the root 2 to q within bracket square root of 2. Yeah, q within bracket square root of 3 is another such field. Yeah, you can have many such examples of fields. Okay, there are things called algebraic numbers and this, that. Uh, uh, when you look at rational numbers and then you go to real numbers, yeah, and from real numbers, when you algebraically close it, you get the complex numbers, which is also another example of a field. This sort of indicates as if fields are right, like, real numbers have infinitely many points, complex numbers have infinitely many points, rational numbers also have infinitely many points, but they are countably infinitely many. whereas real numbers and complex numbers are uncountably infinitely many. That sort of indicates as if fields always have infinitely many elements in them. That's not true. There could be fields with just finite number of elements. Yeah, there could be a field with just two number of elements. Just 0 and 1. Look at 0 and 1 and define multiplication by and addition by XOR, exclusive OR. Define addition by exclusive OR and multiplication by and, you get a field. Yeah. In fact, there could be fields with where P is a prime number and Q is any positive integer. There can be fields, there are fields with exactly P to the Q number of elements. Yeah, so these are called finite fields. So field is something where you can, because there is this is closed under addition, there is additive identity and additive inverse, so you can do addition and subtraction. Because it is closed under multiplication, is a multiplicative identity and has multiplicative inverse for every non-zero element, you can also do multiplication and division. Yeah, division by non-zero elements. All of these four operations can be done. So when all these four arithmetic operations can be done, it's a field. Now think of a field, but now make the conditions a little weaker. So you get bigger collection of things, right? Yeah, some things which may not be fields may turn out to satisfy a lesser number of properties. Yeah. Well, how do you lessen this number of properties? Well, you just take out the multiplicative inverse idea. All other properties you keep, but don't say that every non-zero element has a multiplicative inverse. What you get is a ring. It's a commutative ring. Yeah, when the multiplication is commutative, it's called a commutative ring. A ring doesn't really have to have commutativity for its multiplication, but the kind of things that we have seen, they are all commutative rings. So that commutativity is there. Example, think of integers, positive, negative integers. The set which is denoted by Z. That's a commutative ring. It's not a field anymore. Why? See, under addition, it's closed. There is additive inverse 0, as additive identity 0. Every number X has an additive inverse minus X. Yeah, so all addition, all properties are there. But what about multiplication? As I said, multiplicative inverse. Do we have multiplicative inverse for every non-zero element? No. If you have 2 is an integer. What is its inverse? We know from our experience with rational numbers that the inverse is 1 by 2. Yeah, reciprocal of 2. 2 inverse, 1 by 2. Is 1 by 2 an integer? No, it is not. Yeah. So 1 by 2 is not in the set of integers. So it's not, doesn't have a multiplicative inverse. 2 doesn't have a multiplicative inverse. Neither does 3, neither does 4, neither does -2, -3, -4. None. Only 1 and -1. These two guys have multiplicative inverses in the set of integers. Only these two guys, not all non-zero guys. So therefore, it's just a ring. Likewise, polynomial, if you look at the set of all polynomials, what are polynomials? They are finite expressions of the form a0 plus a1x plus a2x squared plus ... plus an x to the power n. N can be anything, arbitrary positive number, non-negative number. Yeah. But it is finite. It is such a finite expression, which is actually, in fact, a linear combination of the symbols 1, x squared up to x to the power n. Such an expression is called a polynomial. And when you collect all those expressions together in a set, that's called the polynomial ring. Why? You can easily check that it's a ring. Why? Look at addition. 2 polynomials added together gives another polynomial. 2 expressions like this, when you add, you get another expression like that. Yeah, what do you do? You look at the same powers, yeah? Those coefficients you add. That's it. Those coefficients which are missing from one polynomial but present in the other polynomial, you treat those missing guys as 0. And then you add them together, yeah? So, close under addition. Is there an additive identity? Of course, 0. 0 is a polynomial. It's added to any other polynomial, gives me back the other polynomial. So additive identity is there. Additive inverse, of course, take a polynomial, just negate the signs. Just change the signs of every coefficient. That's another polynomial, which when added together gives you 0. The additive identity. It's closed under addition, has additive identity, has additive inverse as well. Now multiplication. Take two polynomials, multiply them. It is also another polynomial. Formula is a bit complicated, yeah, because how do you get the coefficients for a particular power? Look at that power and see how many possible combinations are there for these two products to give you that power. Yeah, if you have 1 plus x, a polynomial, and 1 plus x squared, the other polynomial, how do you get, if you do the product, then it's, x cube comes from x and x squared, so its coefficient is 1. X squared comes from 1 and x squared, so its coefficient is 1. Yeah, so x cube is there, x squared is there, x will be there, x times 1, and 1 is also there. So it's 1 plus x squared plus x cube. That's how it's going to look like. Yeah. So closed under multiplication. Multiplicative identity, of course, 1. 1, the number 1 is a polynomial. Yeah, it's a multiplicative identity. Now, what is there a multiplicative inverse? Now, that is tricky. That is tricky. When is there a multiplicative inverse? Suppose we take x. Is there a multiplicative inverse to x? We know that it should be x inverse, but is x inverse a polynomial? No, it's not an expression, the kind of expression that we are dealing with. The expressions are, remember, a0 plus a1x plus a2x squared and so on. There is no place for an x to the power minus 1. So it is not a polynomial. So x doesn't have an inverse. Neither does 1 plus x, neither does 1 plus x squared. All these guys don't have polynomial expressions for their inverses. One might say, okay, take 1 plus take 1 plus x, and inverse is 1 minus x minus plus x squared minus x cubed and so on. That infinite series. No. First thing, that infinite series is an infinite series. It's not a polynomial. Yeah. So therefore, we cannot talk about such things. And also, I mean, this makes make this, well, that's really not the matter here. I was talking about, I was thinking of telling you about the convergence issues, but that is not a problem here because we're dealing with only formal power series. But remember, power series is not a polynomial. An expression of the type alpha a0 plus a1x plus a2x squared plus a3x cubed plus dot dot dot. That's not a polynomial. That's a power series. That's a different object completely altogether. Our polynomial set Rx does not include these guys. So therefore, 1 plus x is not invertible in the world of polynomials. So that's why the set of polynomials is a ring. Yeah. Can you get a feel out of it? Yes, you can, by taking ratios of polynomials. Those are called rational functions. Just like you can go from z to q, integers to rational numbers, in the same manner you can go from polynomial rings to rational functions. Yeah, that's a field. This guy is a ring. What is the utility? Why is it important? Well, it's immensely important, as we have seen in the behavioral theory course, in this NPTEL course, that all those differential equations, difference equations, this, that, all of those actually ultimately boils down to doing some polynomial algebra. Yeah. With their various algebraic techniques, Euclidean division algorithms, Smith canonical form, all these things are immensely powerful. And utilizing those things, one can actually solve differential equations. That's the power of polynomials. I mean, it's very hard for me to actually list out, give an exhaustive list of things where this becomes important. It is extremely important in various different aspects. For those of you who have done some control theory, some undergrad control theory, you remember when you talk about when you talk about Laplace transforms. Laplace transform essentially utilizes this polynomial algebra. Yeah, the kind of signals that we deal with in electrical engineering, when you look at their Laplace transforms, it turns out that they are ratios of polynomials, rational functions. And these rational functions, then you use this transfer function techniques, yeah, to come up with all sorts of solutions to real life engineering problems. I mean, how do you control how do you control the noise cancellation of a headphone? Yeah. Or how do you control the robotic arm? Yeah. And nowadays, when you are dealing with, multi-agent systems, how do you do these controls? You use all these transfer function techniques, and those transfer function techniques are made possible because you have polynomials at your disposal. Yeah, the algebra of polynomials at your disposal. That's the utility, that's the importance of polynomials. Okay, there is one more question. I hope this answers your question, Mr. Praharaj. There is another question now. Maniram Krishna Adike. Yes, good morning. How to apply the data-driven framework for MIMO-based systems? Well, I don't remember exactly what approach did I take in the course, but I think I did not consider CISO all the time. Maybe the examples were all CISO, but the approach per se was in general MIMO. Yeah, multi-input, multi-output. So the only difference that comes out is that, the way you write down those Hankel matrices. Yeah, Hankel matrices are usually usually written down as W0, W1, W2, dot, 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 W some number, then the W1, W2, W3, dot, 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 like that. Yeah, and each W contains all these inputs and outputs. If it's a CISO system, then each WI is a two-tuple. On the other hand, if it's a MIMO system with P number of outputs and and M number of inputs, then it is P plus M, which we call Q. So each one is a Q tuple. So ultimately, the matrix that you get is a block matrix where each entry actually is a Q tuple. Yeah. So therefore, it doesn't make much of a difference. And in fact, I think I did do this MIMO thing because ultimately, when we talk about this, these indices, the fundamental indices of these restricted behaviors. Yeah, those fundamental, the dimension of BI, right? Remember the dimension of BI, which we call DI. And then we look at D0, D1, and D2, and we saw that these dimensions keep increasing. And then you look at the difference of the dimensions, which we call rho. And then we saw that this guy saturates, yeah. And this rho infinity is the input cardinality that comes out to be M, and that number is the number of inputs. So of course it is MIMO. Yeah. So there's one more question. I hope this answers the question of Maniram Krishna DK. Then there is another question from Gautam Sinha. What are linear matrix inequalities in control? Yes. The very first example of a linear matrix inequality that you see in control is in the form of Lyapunov inequality. Yeah, when you have if you have a system x dot equals ax, yeah, and you would like to have a certain stability, asymptotic stability of this system, you can use Lyapunov theory. And if you take a Lyapunov function which looks like x transpose px, where p is a symmetric positive definite matrix, then it boils down to solving for one such unknown p, positive definite symmetric positive definite p, such that A transpose P plus PA is less than or equal to 0. That's a linear matrix inequality. This is the first example of a linear matrix inequality that we see in control. There are several others. In fact, the conventional robust control is actually a study in linear matrix inequalities. I'll give you an example. Suppose you would like to find out the H infinity norm of a transfer function matrix, which has a controllable observable state space realization given by x dot equals ax plus bu, y equals cx plus du. For such a guy, if you would like to find out its H infinity norm, then it turns out that there is a linear matrix inequality, yeah, called coming from the bounded real lemma, involving a parameter gamma. Then the job is to minimize gamma such that this linear matrix inequality is solvable, is feasible. There is a P, positive semi-definite P, such that this linear matrix inequality, weird looking linear matrix inequality, I can derive it, but I don't think it is worth right now. But you can just look up bounded real lemma and you'll find this one. This is another example which is very similar to this one called Kalman Yakubovich Popov lemma, KYP lemma for passivity. And that also comes out as a linear matrix inequality. Similar. Then there are these robust control techniques which once again come up as linear matrix inequalities. Yeah. I hope that answers your question, Mr. Sinha. Thank you. Thank you, Mr. Adike. I think it's almost time for us to close the session. Um, Perhaps one more question I can take. I hope you are enjoying the course. You're learning something new from the course. I would like to have your feedback. So write whatever you are thinking of about the course and send me your feedback. Thank you. Thank you for attending this live session. It was very nice to interact with you. Thank you. Thank you. Yes, of course. Thanks. Okay. Bye. Take care.